All right, welcome everyone. Thanks for joining us today. This is Introduction to Sparkview. And during this session, we are going to jump through a number of activities. My agenda is to do 3 activities in the hour we have together. The first is coffee cooling, where we're going to take a look at the essential features of Sparkview. We're going to do a little investigation about some everyday phenomenon here with temperature. And the primary point of this is to learn some things about the Sparkview interface, the software from Pasco for data collection across the grades, sciences, and devices. Then we're going to dive into a special case. When do you need to take more control over measurements in the form of a quick activity where we look at the forces involved with a cart collision. And the final activity will jump to a different way to collect data as we investigate the relationship between the pressure and volume of a confined gas. Throughout these 3 activities, I'll be doing quick interludes to introduce you to topics like saving and sharing files, the platforms that are supported for Sparkview, which sensors work with Sparkview from Pasco, and where can you get experiments for you and your students. So let's dive directly into coffee cooling activity. The coffee cooling activity has a scenario here I'll pose. Imagine that you're going to school and you want to stop at your favorite coffee shop near school to grab a coffee, and it's a nice hot coffee, and you want to keep it as warm as possible on your short commute to school so that when you get to school, that coffee is still warm. And you happen to like a lot of cream in the coffee, cafe au lait proportions of cream. So you have 2 options if you like cream in your coffee. You could add that cream at the coffee shop and then commute to school with the cream already in that coffee. Naturally, this coffee is going to cool as you go to school. Or the alternative is to keep that coffee black as you commute to school, same duration of time as you commute, and then add the cream once you get to school. So in the end, you're drinking coffee with a lot of cream in it, the same amount of cream. But the question is, in which of these scenarios, adding the cream at the coffee shop or adding the cream at school, will the coffee stay warm the longest? So it's essentially a question of which of these 2 scenarios is true. The temperature of the coffee whose cream was added at the shop be greater than that of the coffee whose cream was added at school, or vice versa? And we're aiming to make the coffee as warm as possible when we get to school by choosing one of these 2. So I'm going to jump over to Sparkview, and we're going to try to answer this question through some investigations. And of course, the real point of this is to learn some Sparkview tools and how we can make measurements across the sciences with Sparkview and Pasco sensors. So I have out here a little beaker of room temperature cream. You might think about your prediction. Do you think it'll make any difference if I add the cream to the coffee first, or I add it at the end? We're going to do that shortly, and I have a beaker here that will represent our coffee cup. It's currently empty because I'm going to put some hot coffee in it briefly. And the sensor we're going to use to make these measurements is the wireless temperature sensor. We'll be putting that into the cup of coffee and measuring the temperature when it's black coffee and when we add the cream and after, to see if we get different cooling rates between these 2 scenarios. So off screen here, I'm going to prepare some coffee. Actually, first, let's set things up so that we have the coffee as hot as possible. The wireless sensors from Pasco are generally white, and they have their own power. This one has a coin cell battery in it. So I'm going to turn the power on to that sensor, and I see the Bluetooth light blinking red. And let's draw our attention now to Sparkview here. This is what we call the welcome screen. And the welcome screen gives us some paths, some choices of ways to use Sparkview. Now, we're going to collect some data from a sensor, and often it's the case that if you're doing your own experiment, you want to choose this sensor data path. So I'm going to choose sensor data, and it's going to open up a screen where I can configure which sensors and measurements I'm using. Now, since my temperature sensor, and in fact some other sensors around me, are on, I see that this panel to the left opens, and it gives me a choice of the wireless devices that are in my vicinity. Now, I have a temperature sensor, so this is my temperature sensor. I'm going to click on it, and it's going to make a connection to the temperature sensor between Sparkview and the sensor. And our wireless sensors use Bluetooth 4 or Bluetooth Low Energy. And the benefit of Bluetooth Low Energy is that this connection can be made in the software itself. I don't need to go into the settings on any particular device. It doesn't matter what platform I'm running Sparkview on. I can connect directly to these wireless sensors all within Sparkview. So now that I have my temperature sensor connected wirelessly, I see that the center panel populates with that sensor that's connected and shows me the option here to select a measurement. Now, by default, the temperature measurement is selected. Since that's the measurement I'm interested in, I'm going to leave that checked, meaning that's the measurement of interest. And I'm going to direct your attention to the upper right here, where we have some templates into which we can place temperature readings. And there are a variety of setups here. We can have just a graph or a table and a graph, a variety of displays we can use to visualize these temperature measurements that we're about to record. I'm going to choose the upper right option as I see it here, table and graph. And let's see what happens with temperature selected in the center column when I select the table and graph template in the upper right. Well, Sparkvue builds a lab. It's called the Sparklab. It has one page right now, and on that page, it has put the two displays I requested from that template. You'll see on the left side, I have a fairly small table occupying the left third of the screen, and it has two columns, time and temperature. And temperature, of course, is that measurement that I requested. It also fills a larger portion of the screen on the right with the graph that I requested, and we see that its y-axis is the temperature measurement. We can't see its x-axis because my screen is fairly narrow, and because this thing we call the graph toolbar is open. So I'm going to close the graph toolbar by clicking on that button. Every display has a toolbar that you can toggle open and closed with the button in the lower left of that display. And when I toggle close the graph toolbar, we can see that the x-axis is time. So I essentially have a table and a graph display of the same items, time and temperature. Now I'm going to prepare the coffee here, making sure it's very hot, and fill in the beaker with a known amount of coffee. This will be filling up the coffee at the coffee shop. And while I'm doing that, I want you to notice that even before I record any data into these displays, you can see what the current temperature of my temperature sensor is. My temperature sensor is currently in the air here on the tray, and in the lower left of Sparkview's screen, you can see what we call the live data bar. And this shows you that the temperature reading right now is 21.3 degrees, vacillating a little bit here, 21.3, 21.4. So let me put some hot water, rather hot coffee into that beaker. And I'm going to put about 150 milliliters of quite hot coffee. A bit more, and put that back on screen and put the temperature sensor in so that we can make sure we're measuring the temperature of that coffee. All right, so there's 150 milliliters of coffee. As I put the temperature probe into the coffee, you can see that that live data bar begins to update, and you'll see it increasing and increasing and increasing. That's because, of course, we have to get the temperature probe to the temperature of the coffee. They need to reach equilibrium. So we can see that that temperature probe, stainless steel probe, is heating up as shown in the live data bar, and should be slowing down and eventually start cooling down. Now I want to note that the temperature probe itself measures the temperature about 0.5 centimeter from the end of the probe. So we're in the coffee there, and we see it might have plateaued here at 77.9. I want to look at the live data bar here and make sure it continues back down. And when it gets to a known value that I can remember, maybe 76.5 degrees, I'm going to begin recording because we want to be able to replicate this. So we're at 76.9. When it gets to 76.5, I'll begin recording by pressing this green start button that's in the bottom center of the Sparkview display. So we're at 76.5. I've pressed record, and now let's take a look at the displays above. We can see that at a regular pace, the rows of our table are populating with time and temperature values, and we can see that the temperature is being graphed here. Now I want to add the cream at the coffee shop, and I'm going to simulate that by adding my cream at about 20 seconds. So we're almost at 20 seconds here. I'll add the cream. And this is our first trial here, adding the cream at the coffee shop and now commuting to school as that cream is in the coffee. You can see it mixing, and we're getting a lower temperature, of course, because this cream is at room temperature. Now, a few things to talk about as we wait. I think I'll go about 2 minutes. Let's pretend we have a very short commute to school. So I'll go to about 120 seconds, at which time I will stop collecting data. But as we get more data points on the graph and in the table, you can see that the graph has changed its behavior so that it automatically scales its X and Y axes so that the data we're collecting fills the screen. We'll talk a little bit about how we can change our view of that graph, but you can see that we're getting these data points filling the screen, and the graph is dynamically adjusting its axes so that we can see all of the data being collected. Now, another thing to note is that by default, Sparkview's graph shows data points as dots connected by straight lines, and we're collecting data so rapidly it looks like a blur here, except when we saw the drop. You can see in this region here that we have dots connected by straight lines. All right, so we're going to 120 seconds. You can see the coffee is continuing to cool. We'll ask some questions about concepts like rate. And as we do this, think about what your prediction is about what we'll find. So at 120 seconds, I will stop this set of data. Each set of data we collect between pressing start and stop is called a run. And you can see in this thing we call the graph legend that each run has a unique name, enumerated run 1, run 2, and so forth, and a unique symbol and color. This one is blue. So as we approach 120 seconds, I will go ahead and press stop when we get there. Right about there. All right, so run number 1 represents the temperature, the final temperature here, which we can see in the table and in the graph visually when we added cream at the store. at the coffee shop. Now, before we proceed, I want to do a little analysis of this. We're going to dive into some quantitative analysis tools in a little bit, but there are some tools in the graph toolbar that'll help us remember what has happened here if you have a short memory like I do. One thing I might want to note is if I came back to this data in a week, what happened at this interesting point? Well, let's first learn how to change our view of the data. It's good that by default, the graph rescales itself so we can see all the data, but sometimes we want to focus in on a particular point. So what I can do is with my regular cursor, I can just click and drag, and it's almost like I'm moving a piece of traditional paper graph paper on the tabletop, just translating up, down, right, left, diagonally, and so forth. So I can put this little cusp where I added the cream in the center. And if I want to zoom in, I can take my regular cursor or finger if you're on a touch screen, and I can click on drag on the numbers on the x-axis or on the y-axis. So here's dragging away from the origin on the x-axis. It kind of stretches it as if my graph is made of a rubber sheet, and I can do that to move away from or toward the origin. And this is essentially compressing the view in X or Y, allowing me to zoom in. So if I'm looking at this cusp and I want to remember a week from now what happened there, it would be nice to be able to add a label. So with the graph toolbar open, I can see that there are some tools here. And if I have a mouse-driven device like this Windows computer, I can hover over a particular tool and it tells me what a tooltip is for that. I'm going to go to this letter T, which is called Add Annotation, and I'll click on it. And it pops open this screen that allows me to add a note. So I'm going to add a note that says added cream. When I press OK, this note drops somewhere on my graph. It's attached to the graph by a little gray handle, and thankfully I can move that gray handle around and drop it on a relevant data point. So if I release the gray handle close to the data point that I'm interested in labeling, you'll see that the gray handle snaps to it. I can also move the label itself if it's out of the way or need a better view of it. So I've zoomed into that data using manual scaling and zooming on the graph Y and X axes, and I've added an annotation using the annotation tool. I'd like to zoom back out now and start to contemplate collecting a second run of data. The way to zoom back out immediately to see all your data is to use another graph tool. It's the leftmost and probably the most used tool in the graph toolbar. If I hover over it, you can see it's called Scale to Fit and shows 4 little arrows shooting off. So I'll scale to fit, and we're back to viewing all of the recorded data, including, of course, my little annotation here when I added the cream to run number 1. So back on the tabletop here, let me prepare the second beaker of coffee. I have the hot coffee here still. I'm going to refill a new beaker here, a room temperature beaker, with the same volume of coffee. And in this second scenario, we are going to measure the temperature of the coffee when we add the cream at school. So let me go ahead and put the temperature probe in that new coffee. And we're hoping that I didn't cool down too much. All right, looks like we're going over 76.5 again, was it? I'll use this tool, which I'll talk about later. Yep, about 76.5. So it's quite a bit over 76.5, and I'd like to show you some more advanced features in Sparkview that will let me more quickly or more easily record the data I want. I have some very prescribed conditions here where I wanted it to start at 76.5 and stop after 2 minutes. So I'm going to open up this little sampling options, and I can have a start condition where I start when the temperature falls below a certain value, in this case, the target value of 76.5. And I can also have stop conditions, for example, one that's measurement or time-based that stops at 120 seconds. I'm speeding through this, did a little quickly, but I wanted to make sure I didn't miss the temperature there. So I'm going to press start. And because I have that start condition of the temperature falls below 76.5, you'll notice that it's monitoring the temperature, as I can see in both displays, but it's not actually going to begin recording until that condition is met. This can be handy using start and stop conditions for long-term experiments like this one to stop at a certain time, or it can be handy if you have a very fast experiment, something that's too fast for you to respond to, as we'll see in the second activity. So let's wait for that temperature to fall below 76.5, which is our start condition. And in this case, we're going to add the cream when we get to school. So I'm going to add the cream about 20 seconds from the end of our 2 minutes. So we're approaching 76.5 degrees. And as soon as we do, it should automatically begin recording that data. There we go. So we've reached 76.5. We can see it continues to cool, and we get a new run of data as shown by the legend in both the table and the graph. This new run has a different symbol in the legend and has a different color. So we have the cyan run representing run number 2. Now, the first thing you might notice is that run number 1 disappeared in our graph? Well, by default, Sparkview's behavior is to only show the most recent run, but I'd really like to see both runs at the same time here. So I'm going to show you that in the graph legend, there is a checkbox to the left of each run name. And this checkbox represents the visibility of the run. And since only the checkbox next to run number 2 is checked right now, only run number 2 in cyan is visible. If I want to see run number 1, I simply check it, and we can see in darker blue, we have run number 1. Now, I'm going to scale to fit so we can see the entirety of run number 1. And now we can see it's kind of a race here. So the question is going to be, when I get to 100 seconds and add the cream, that is, I'm at school and I'm ready to enjoy my coffee, what's going to happen to the final temperature? Is it going to be different from or the same as the dark blue run? All right. So we're going to talk a little bit about the table in the third activity. I don't find a lot of value in the table when we have a lot of data points, hundreds of data points as we do here. But there are experiments, as we'll see in the third activity, when you're just collecting a few data points, and the table can be integral to that. For activities like this with hundreds of data points, I find the graph very handy to use. Allows me to see the entirety of the behavior. So I have my cream ready, and when we reach 100 seconds, I will go ahead and add it. This is our drive to school here with the black coffee. And when we hit 100, I'll go ahead and add the cream right about now. All right, same amount of room temperature cream to the same amount of hot coffee. And let's go ahead and wait for our stop condition to kick in. Remember, at 120 seconds, we should see what happens. Very close here. All right. So the stop condition happened automatically. And if we want to figure out what happened here at the very end, we might want to go in and pan over and use our scaling. All right, so might have been too close to call here. But let's look at some of the behaviors, and let's look at some of the quantitative tools now we can use to analyze the data once we collected it in the graph. One natural question would be, well, what are the final temperatures of these two runs in this case? So let me introduce you to a tool that's used very frequently, and that is our coordinates tool. Here's the coordinates tool in the graph. And if I click on the coordinates tool, you're going to see that much like the annotation, it pops open a label, and it allows me to reposition that label by grabbing the gray box and dropping it on any particular data point of that run. Now I can also nudge it point by point. So let me just go ahead and grab that and go to the very final data point, which we can see for the run number 2 is at 120 seconds, 59.4 degrees Celsius. I'm going to scale back out here and show you that I can also add another annotation. I can have as many annotations as I want. So I might want to add an annotation to the cyan run number 2 to indicate when its cream was added. You already know that I can add this annotation via the graph toolbar, but let me show you there's an even quicker way, in my opinion, to add many tools to points on a run. And that is to go directly on the point that you want to annotate and click on it, where you'll temporarily see an orange dot. And you'll notice some pop-up tools, and you might recognize a couple of those tools. I could add a coordinates tool, just as I did from the toolbar, and I can add an annotation here. So I can add cream in this case as well, right? So 2 ways to use many of these tools, including the annotation tool and the coordinates tool. Just as I added that run there, I'd like to add an, as I added that annotation, I'd like to add a coordinates tool to the dark blue run. So let me get a better view of it. And if I go to the coordinates tool and turn it on, I'm going to have a little dilemma here. I want to annotate run number 1, the blue run. But when I turn on that tool, I just get another annotation tool whose color tells me that it's associated with run number 2. So another important concept in the graph when you have multiple runs visible is that only one run is active at a time. And this active run is shown in the legend by having a red box around its symbol. By default, the most recent run is the active run, and you can see that the red box is around the most recent run, run number 2. It's simple to make a previous run active, and you simply click on the symbol for that run. And now if I add a coordinates tool, either via the graph toolbar here, let me delete that, or directly by clicking on a data point and selecting coordinates, you can make sure that you're analyzing the run of interest. So a key idea here is when you have more than one run, before you use the tool, make sure you know which run is active by selecting it in the legend. So I'll zoom back out here, and to be honest, this isn't the result that I usually get. It seems a little too close to call here. So we might want to look at doing this a couple of times. And since data collection and visualization happens so quickly with sensors, we could do so. But I'm going to zoom back out, and we might have some other questions about, well, what's the real difference between these two scenarios of adding the cream at school or adding the cream earlier at the coffee shop? And among types of things we might want to analyze to figure out if we have a genuine difference between these two is how much the temperature changed during the drive. So if we think of this portion here from about 40 seconds to 100 seconds, we might ask the question, well, during that time, how much did the temperature decrease? Is there a relevant difference between the two during that time? So I'm going to drag my coordinates tool back here until I start at 40, and I could add as many coordinates tools as I want to look at that temperature difference and use the X and Y coordinates here to figure that out. But the coordinates tool has a very powerful but hidden feature called the delta tool within it. If I click on the coordinates tool label, you'll see there's a gray box to the left that has the Greek letter delta for difference. And if I turn on the delta tool, I get a second handle. I can drag out that second handle to a different data point. And what's nice about the delta tool is it tells me what the change in X, that is the change in time in this case, and the change in Y are. So I can see over those 61 seconds, I can adjust that to 60 if I need to. I had a temperature decrease, the y-axis, delta, of -2.4, or a change of -2.4. I could do a similar thing, first making sure I make run 1 active. I could turn on the coordinates tool directly and then turn on the delta tool and look at the same time period and see that in this case, the temperature change was a little less. It was only 1.9 degrees Celsius decrease. So when I usually see significant differences, measurable differences between these two, we can kind of hone in and say that, some rate of heat difference was evident when we were driving. Usually that results in the coffee that had the cream added at the coffee shop to be cooler. So maybe I didn't wait quite long enough, or maybe this is just a trial that I need to redo. When we're talking about rates, which we can determine indirectly from the delta tool, I want to show you one more tool that can be very powerful, and that is to make a linear fit to a portion of data. So let's say I wanted to get the average slope during the same time period for run number 1. To make the screen cleaner, I'm going to delete my coordinates and delta tool, and I'm going to turn on a new tool from the graph toolbar called the linear fit. Here's the button for that. And since run number 1 is active, I know that this linear fit, when I press on it, is going to apply to run number 1. Well, it did apply to run number 1, as I can see from the color here, but it's applying to the entire run. So it's doing its best to do a linear fit, best linear regression to the entire run number 1. That's not what I want, though. I want to do an analysis of, say, the time between 40 and 100 seconds instead. So what I can do is change what set of data within run number 1 the linear fit and other tools is applying to. The way I do that is to make a selection of the data in run number 1, but I have a little dilemma because we already know that my cursor is a mover, not a selector by default. But if we come over here to this second button in the graph toolbar, it's a toggle that allows the behavior of our cursor to change. By default, it's a mover, as shown by this button on the left, the move tool. But if I click on the right portion of this, it will toggle over to be a select tool. So now if I go with my cursor in the graph, I can click and drag a box around that portion of data. And notice that that linear fit adjusts so that all of the data that's highlighted in yellow inside the box is the data that's analyzed. So now we can see that linear fit is doing a good job of determining the best linear fit to that set of data in run number 1 between 40 and 100 seconds. And of course, I can adjust the selection and the live linear fit updates to reflect whatever that adjustment is to the data inside my selection box. So I think it would only be fair to do that for run number 2 as well. We can see the rate of change here represented by the slope for run number 1 during that drive. I'm going to make run number 2 active, make sure I can see the region of interest, clean things up a bit by clicking on my annotation, my coordinates tool rather, and deleting it. And now let me show you there's another way to apply a linear fit to a region. I could now start by making the region selection first. So I have my select tool active. I can first drag out the box, and when I release it, it assumes I want to do something to that data. One thing I could do is apply a linear fit. And now we can see these contrasting linear fits for the black coffee in the car during the drive and the already creamed coffee in the car. Now, I have a little trouble interpreting these slopes, which would represent the change in temperature in degrees Celsius over time in seconds, but I can make these numbers a little more palatable by quickly changing the units of my time axis. So this is currently degrees Celsius per second. I'm going to go to the time axis label and click on it, where I can change what measurement is being shown, or if I click on this little label, I can change the units. So if I change the x-axis units to minutes, everything updates, including, of course, the x-axis labels. But most importantly, in this case, it also shows me now the slopes in degrees Celsius per minute. A little more understandable, where we can see things were cooling more rapidly for the black coffee in the car than they were for the creamed coffee in the car. So that might give you a clue about the usual results for this, which I'm sorry we didn't quite get clearly in this case. One other way to talk about this, if you're teaching something like Newton's law of cooling, is the farther something is from room temperature, the faster it gets there. So you might know that a linear fit might not be the best way to do this. I just want you to know that you can go in and choose other fits besides linear, and you might be interested in exploring a longer data set of this type of data collection with something like natural exponential to see if that even more accurately reflects the behavior we see here. One final way to think of this is if we know that the rate of heat loss is greater the farther you are from room temperature, one thing we could do is get rid of our selections, and we could ask, so what was the average temperature for the cyan run versus the average temperature for the blue run? To do that, I'm going to turn on one final tool here called statistics. It looks like the Greek letter sigma. And if I turn that on, I can choose from a variety of statistics, including the mean or average value. So I'll turn on the mean for both runs. And as we can almost certainly visualize, we can see that the mean temperature of the coffee when I was driving with it black was significantly higher than the mean temperature when I was driving with it with the cream. So some investigations we can do, not definitive in the science sense in this case. I might need to do it again, and I have no trouble buying some more coffee to repeat the experiment, but hopefully this gave you some exposure to some Sparkvue tools. And we looked at a lot of tools in this case, but to be honest, we could have answered our question with just a few of these tools and knowing the fundamentals of connecting a sensor, creating a visualization, and recording a run or two of data. So this is, to be honest, the majority of what you do across all labs and all subject areas with all of the sensors, not just temperature in this type of investigation. So let's return to the slides here and talk a little bit about Sparkvue. I mentioned Sparkvue without really telling you what it can be used on. The reason for that is it can be used on pretty much everything used in education these days. So if you have Android phones or tablets, maybe even the Android phone in your pocket, you can get Sparkvue on the Google Play Store. If you have an iPhone or an iPad, you can get it on the Apple App Store. And if you have Chrome OS, like a Chromebook, you can acquire Sparkvue on the Chrome Web Store. And the nice news is, for all of these three platforms, the Sparkvue app is completely free and full-featured on the respective app stores. So if you and your students are using these platforms, you can get Sparkvue right now on the respective app store. Sparkvue is also available for Windows, which is where I'm using it right now, and for Mac OS. So we hope that these represent the competing platforms that you're using in your schools. One difference is that you cannot get the Sparkvue app for Windows and Mac on their respective app stores, but you can get it at pasco.com/Sparkvue if you go to the downloads tab of our Sparkvue product page. It's important to know that there's a free trial of Sparkvue on Windows and Mac, but ultimately, if you want to use it past that 60-day trial period, it's a licensed piece of software. So completely free from the respective app stores on Android, iPhone and iPad, and Chromebooks, and a licensed app for Windows and Mac. I should also note that if you happen to have a dedicated Pasco data logger, like the Spark LXi2, Sparkvue, of course, comes installed on that device. All right, so we have a file with some data we might want to reflect on in the future or add new trials to if we want to get more definitive results. So I'd like to talk throughout about some ways that we can save and share our information in the Sparklab. So I'm going to return to Sparkvue and show you one option here. I'm going to show you that we can go to the main menu of Sparkvue, and we can click on it and choose the option to save the file. So let's see what happens when we choose to save a Sparklab. I get the systems dialog. I'll go ahead and click on the desktop here, and I'm going to save this file as coffee cooling data. And what you'll notice is that this saves as what we call a Sparklab with the extension .sparklab. So I'll go ahead and save that. Let me tell you a little bit more about Sparklabs. Sparklabs are the proprietary form of all the information in your Spark file. So they are proprietary, so it requires Sparkvue to reopen it. But the good news is that Sparkvue on any platform. So I could send this over to Dan's iPhone, and if he has Sparkvue, the free app on his iPhone, he can open up this lab and do his own analysis and to continue collecting data if he had a temperature sensor. So the Sparklab is a complete record of the file. It has everything about it, including the setup, the displays, all your data, all your analysis. And it's a great way to continue your analysis, maybe outside the lab, or to add additional runs in the future. But again, you do need Sparkvue to reopen that file. To show you how to reopen the file, I'll go back to Sparkvue. I know I've saved this. So if I close Sparkvue and relaunch it, this could even be on a different device on a different day. From the welcome screen of Sparkvue, one way to get there would be to choose Open Saved Experiment. And since I saved it on my desktop, we can see that Sparklab there. And when I open it in Sparkvue, we see it returns to that same state, all the data, all the displays, and all the analysis. All right, so that is saving and reopening a Sparklab file. Now, our goal is to make Sparkvue work the same across platforms. So everything except that saving that I showed you is the same across all of the supported platforms for Sparkvue. But as you might be able to guess, when we get to specific devices, Windows is not going to open up the Google Drive folder, but a Chromebook is. So there are a few differences in the opening and saving of files. That's where things are different across platforms, but the core of connecting sensors, creating displays, collecting data, and analyzing that data is the same across platforms. I just want to note, if you're on a phone or tablet, you'll find the options we'll talk about for saving and sharing in a dedicated button that looks like this, called the sharing button. All right. So one question that also comes up is, hey, if I have 2 temperature sensors, could I do this experiment with 2 temperature sensors simultaneously, perhaps buying 2 cups of coffee at the same time? And the answer is yes. We're not going to do that, of course, but I just want to show you the mechanics of using multiple sensors. So if I go back and launch Sparkvue again, I'm going to create a new file in the same way we did before, but I'm going to show you how easy it is to connect multiple sensors, and perhaps more importantly, to distinguish between multiple sensors. So I'll choose sensor data again. And this time around, as you can see on the live view here, I'm going to turn on 2 temperature sensors, 2 wireless temperature sensors at the same time, and they're both going to show up in this list of devices that I could connect. Now, this is also going to happen when you're doing a single sensor experiment in a class full of sensors. So it's important to know how to figure out which sensor is yours or which sensors are yours. So if we focus in here on the sensor itself, you'll see that the sensor has a label next to its Bluetooth button, and that label has a 6-digit ID, which should correspond, when the sensor is on, to a 6-digit ID that you see here in the list. So if I wanted to connect this temperature sensor, I would merely click on it in the list after I've identified it from its 6-digit ID, and it will connect to Sparkvue. And after this sensor has connected to Sparkvue, it won't be available for anyone else, because the sensor can only connect to one computer at a time. But that does not prevent that computer from connecting to multiple sensors. So I could look at my second sensor here, 463596, that's it. By the way, the closest sensors will show up at the top of the list. I could connect to that, and I can have multiple sensors connected if my experiment requires it, even multiple sensors of different types, so temperature and pH, or temperature and CO2. You'll notice that I have both measurements checked here in the select measurement for templates. And now if I choose that same template I did before for table and graph, you'll notice that it recognizes my multiple temperature measurements and allows me to collect from multiple sensors simultaneously. So a little variation there if you're using experiments that require or could benefit from multiple sensors. All right, we're going to quickly jump to a quick experiment, and I'm going to pose a scenario for you. I'm going to change your view here so that you're looking at the cart and track system that I have a little further past the end of the table here. And I want to introduce you to what is another wireless sensor, although it doesn't quite look like most of our other wireless sensors. This is our wireless smart cart, and it actually has a bunch of sensors built into it, as we'll see in a moment. But my question of interest is, I've attached to the force sensor at the end of the cart a hard spring. And I'm curious, what are the forces that this cart experiences if I release it on this ramp and let it collide with that end stop there? Can we record the forces that the cart experiences during the very short period of time when it is colliding? All right, so we're going to figure out what we need to know about Sparkvue to change things. But first, let me show you what our dilemma is. So I'm going to turn on the smart cart since it's just another wireless sensor. I'm going to head over to Sparkvue, and we're going to use that same sensor data path because I'm most interested in just quickly visualizing data from a sensor. So I'll choose sensor data, and my smart cart, which uses Bluetooth low energy, just like temperature, will show up here in the list. So I'll connect to my smart cart. And once it connects, I'd like you to see how many measurements are available from this in the center column that the configuration screen shows us. So we're making that wireless connection. The center column populates, and each of these blue bars is an actual physical sensor on the device. So we have the ability to measure the cart's position from an optical encoder on the rolling wheels. We have the force sensor, which is of most interest here, where I have my spring connected. We actually have a built-in 3-axis accelerometer and a built-in gyroscope here. So the cart has the ability to make all of these measurements, only a few of which we might be interested in this activity. But for now, let's focus on force. So I will unselect position. That's not what I'm interested right now. And I'll choose force, and I'll head over to a template. This time around, let's choose digits and graph. So it creates a digits display that will be the current force reading. And on our graph, we have the selected measurement from the sensor, force again versus time. All right, so I'm going to leave everything at the defaults, just like we left everything at the defaults for our coffee experiment. And I'm just going to collect a run of data here and see if this records the collision forces well. So we're going to have to make a judgment call here. So with the cart at a fixed distance up the track, I'll go ahead and press start, release the cart, and press stop after the collision. Let's scale to fit here and take a look at the data and see if you think this accurately represents the forces you imagine happening while that cart was colliding with the end stop. All right, well, we can see it's a pretty flat, not quite a zero force for a while, and then force goes quite negative, almost negative 3.5 newtons, and that goes back up. But there's only one data point here. Now, you might not know what to expect, and in circumstances like that, what I like to do is repeat the experiment, because if I'm accurately getting data reflecting this collision, this should be repeatable, right? So I'll go back up to the same mark, and let me hit start again, release the cart, and hit stop. And I'll make my run number 1 visible. Let's compare these two. Well, that should have been the same collision, right? I was releasing it from the same position. And we yet again have just one data point that I imagine happened during the collision. It's quite a different value too. So this might be a clue that maybe the data I've collected so far is not accurately representing the phenomenon, that collision of the cart with the end stop. So we're going to dive into Sparkvue now and take a look at how we can customize measurements and sampling rates and things like that to more accurately gather data in some more extreme experiments. These might be experiments whose phenomena happen very fast, like this collision, or things that happen very slow. Maybe you're monitoring the CO2 and O2 levels in a terrarium, and those levels aren't going to change by the second, but they might change by the hour. So we're going to look at ways to customize how we're collecting data from our wireless sensors. So I'm going to collapse this for a moment, and our dilemma here is fundamentally that we're collecting only one data point during the collision. It seems to me like we need to ask Sparkvue and the sensor to collect a lot more data during that collision period. We could use start and stop conditions like you saw in the coffee experiment, and that would be valuable, but we've seen that already. So let's look at some other ways we could do this. Notice that in the lower left, I have this readout that says periodic 20 hertz. And if you know what a hertz is, it's something per second. In this case, this represents the rate at which the smart cart sensors are recording data. So that's 20 times a second, far faster than I could write down data, but still that seems like it's not enough to capture what's happening during this collision, at least in force. So how do we change sample rates? Well, this little dial next to this periodic 20 hertz readout, it returns us to the sampling options where we previously looked at start and stop conditions. But what we're going to focus on now is this thing called the periodic sample rate, which for this sensor is common across all of the measurements for now, at least by default. But I can change it. I can make it slower for longer term experiments where it becomes a sample interval, so 5 seconds between samples in this case. Or what I want to do in this case is make it faster. And I'm going to push it all the way to the right. I can see that I can currently record at 500 hertz from all the sensors in this. And remember, that's a lot of measurements, over a dozen measurements. So that's one thing I want to do. And let's see how it works. So I've now set the sample rate of all the sensors to 500 hertz. I'm going to bring the cart up back to that original same position, and I'm going to press start, and let's see if this resolves our problem. So I'll press start, and then I'll go ahead and get ready. Looks like I have a problem. Let's read this. The system cannot keep up with the sample rate. So I was asking for 500 samples every second from all dozen or so sensors on this. And there's a solution to this, and it is to realize I can either slow the sample rate, or I could say, you know what, I don't need all the measurements this cart can provide in this particular custom application. So let me show you that if I come down here to the sensor configuration or hardware setup button, I can say, you know what, I care about force, so I'm going to leave that sensor on. I'm going to have it broadcast data, but I don't care about the acceleration and I don't care about the rotation. So I'm going to turn those off. You might say I want to turn off the position as well. I'm going to leave it on because some of you might be interested in concepts, more advanced physics concepts like impulse and change in momentum. We might be able to get some information from that. So let's see if I change these two sensors to remain on and the other sensors in the cart to remain off. If I return to the sample rates here, it turns out for smart cart force with others off, I can actually go even faster, but I think 500 is appropriate. And I'll choose the position sensor, and I know the position is not changing as rapidly, so maybe 100 hertz for that. So I now have a mixture of sample rates. Sparkvue gives the ability to control those uniquely. So I'll press OK. Now, as you look at the data I originally collected when runs 1 and 2, our first dilemma was I didn't have enough data points, so we've hopefully fixed that by increasing the sample rate. You might have noticed a couple other things, though, that we can tweak. One of those is that with the cart not colliding, I'm getting a force that is not zero. If you look at the live data bar, or if you zoom into the data, you can see I have a slightly positive force there. So I'd like to define this force before the collision as zero. To do that, I'm going to go to the live data bar itself, which is not just a readout, but also an interactive pop-up menu. And I'm going to choose to zero the sensor now when it's on the track, as you see here. I'm also going to say, you know what, it might be appropriate from the sensor's XYZ orientations on its label to have that be a negative force, but I'd like that to be positive. Maybe some audiences would interpret the positive values a little better. That same live data bar lets me change the sign of the sensor. So the next run I do should be positive forces during the collision. Finally, one more thing, you might be puzzled why I have a digits display when I'm recording 500 samples a second. The digits display by default shows us just the most recent data point, which is going to zoom by at 500 samples a second, but it has a trick up its sleeve. It has a toolbar, but there's only one thing in it. Let me show you what this does. This is our statistics button again. If I'm interested in the maximum value for the entire run, I can tell the digits display to merely show me the maximum up until that time. So in this next run, this will show us the maximum value as soon as that maximum is recorded. All right, so we're back to changing all of those parameters, most importantly, the sample rate. Let's go ahead and hit start and see if we can collect an accurate run. All right, so start and stop. Let's zoom in here to the point of interest during the collision. All right, this definitely tells us that it wasn't a 12 Newton collision max force. It wasn't 3. This is about 14, and indeed 14.02 from the digits display, which of course we could figure out from the graph via the coordinates button if we wanted to. But you can see that when we're taking control of which measurements are recorded, what their sign is, when it's zeroed, and most importantly, the sample rate, we can get the data we need. Now I'm going to spend about 30 seconds here saying, you know what, if you teach a little engineering concept, you might now take this into designing bumpers that reduce the maximum force. If you teach a physics course, you might say, you know what, I'm interested in the impulse during that collision. So I just want you to know, no matter what level you're doing, there are tools in the graph that let us do this. So if I were to open up the graph toolbar and make sure I'm in select mode, I can say, you know what, what's the area under this curve during the force during collision, force versus time. The area is in our statistics tool, and this tells me that the impulse during that collision was 0.33. That would be Newton seconds. And you might then say, I know that's related to change in momentum. I have velocity because I didn't turn off that sensor. So I could add a plot area, show the velocity from the cart, where you can see that change in velocity. And now I could be looking at changes in velocity using tools like the delta tool, and extend that to concepts like change in momentum if I know the mass of the cart. Now, in this case, you can see my changing of the sign for the force was a no-no because this is a negative change of velocity, but we know why that happened and we could change it back to the defaults. So a quick introduction to taking more control over how you're sampling, and it allowed us to answer the question, can we accurately capture the force during this very brief event? All right, so we have another set of data. I'd like to share another way to get this out of Sparkvue, and that is also in our main menu, and it is to export the data. Now, I spent the time to gather this data from 2 sensors, force and velocity, and indeed some others that I didn't turn off. And I've done some visualization in the graph. I've done some analysis. But if my goal was merely to get the data so that I could analyze it elsewhere, I could choose to export the data once I'd collected it. So let me show you what happens when I choose export data. It offers to save for me a CSV file. CSV is short for comma separated values. You might not be familiar with that, but the good news is that's a very generic data format. where the data points are separated by commas, and it's a generic enough format that pretty much any data program can open it. So you can open this in Google Sheets, Excel, any data program is going to be able to open CSV files. So on my desktop, I'll save this as my cart collision data. And it's a CSV file, so I'll go ahead and save that. And my computer happens to have Excel on it, and my Excel is set up to open CSV files. So I'm simply going to double click on that CSV file, and on my computer at least, it's going to open in Excel, and Excel is going to do it best, and it can figure it out. So it has figured out all the columns and all the values across all runs. So here's run number 1's time, force, acceleration, and so forth. Of course, this is a lot of data, and if I want to look at what I really was interested in, and I'd scroll over here to the run number 4, where I collected the force, position, velocity, acceleration. Now, this is just raw data. That means you have the power to do anything with it that you want. You could collaborate with others. You could use it in a program. You could visualize it in a way that Sparkview can't, but the burden is on you to take this data and do what you want with it. So it's a powerful feature, but it's one that doesn't give you the immediate visualization and analysis capabilities built into Sparkview, but it's something that some people want to use. So exporting data here is another option from Sparkview. You can save it as CSV, and if in the odd chance that your data analysis package doesn't accept it, you could alternately export it as tab delimited. All right. So on to our very brief, quick mention. I've mentioned wireless sensors. You may have wireless sensors, fantastic, but you may have Pasco sensors going back to the last millennium. The good news is that Sparkview works with all of these. So we have our wireless sensors that connect via Bluetooth low energy. We had passport sensors starting in 2001. Sparkview still works with all of those if you have an interface, a necessary adapter between the sensor and the computing device. It even works with Science Workshop sensors from the last millennium. So we make sure that Sparkview works with all our lines of sensors. So it's likely that it works with the sensors you have that are older than your students. All right, you want to learn more about these 3 lines and the actual measurements available across the sciences, go to pasco.com/sensors. All right, we have just over 10 minutes, and thankfully this is another quick experiment, but it's one that is a different way to collect data still. So I want to show you on the live view here that I have a sensor here called the wireless pressure sensor, and I have it connected to a syringe of air. This syringe is included with the sensor, and I want to show you how we can determine the relationship between 2 things: the gas pressure, which the pressure sensor can measure, and the volume of air in the syringe, which at least I don't have a sensor for right now. So I want to show you how we can associate data that I type in, like the reading I make from the syringe volume, with sensor data in Sparkview. And while we're doing that, I'm going to show you that we can take control and build our own pages. We don't have to accept those that are provided for us. So let me make sure I save this file as our cart collision Sparklab, because even though I saved it, exported the data, I can't get back to this display unless I save the Sparklab itself. I'll close Sparkview and launch it yet again. And I'm going to show you that I'm going to build my own pages so we can take control over what displays we're using. Build new experiment is the path in the bottom center here. And when I selected it, it gives me some templates that allow me to choose a layout for the displays I'd like on my first page. I'm going to choose this 3rd one down, which is a small thing on the left and a big thing on the right. And once I create that page, it says, tell me what you want to show in each of these placeholders. On the left, I'd like to show a table. It's going to be really useful here as I collect a few data points. And on the right, I'm going to choose the line graph we've been looking at for a while. Now, by contrast to using templates, it doesn't know what to show in these displays. So first, I need to make sure I can connect my sensor to get those pressures. And because I didn't choose the sensor data path, the sensor is not connected right now. So I'm going to turn on the sensor and go to this Bluetooth menu since I'm using a wireless sensor. And I can connect the sensor, the pressure sensor in this case, in the same way I was all the other sensors by clicking on it. Sparkview will make that in-app connection. And once it does, it will move up to the connected devices. And now I can return to my displays and say, you know what, I'm going to select the pressure measurement for the right column of my table and for the y-axis of my graph. Well, that's the easy part, connecting the sensor and getting its measurements. The tougher part that's new to us is, well, how do I type in the volumes? This is what's called user enter data. And in fact, the easiest way to do this is to just start typing. So in the first cell of this empty column, I'm going to say, you know what, I know my syringe goes out to 60 milliliters. So I'm going to type 60 and 55, and I'm going to go down here by 5 milliliters at a time. I think we have time for that. And I know it's going to get tough for me around 15 milliliters, so I'm going to stop there. Now, Sparkvue recognizes that you're entering your own data and says, well, this is user data. I can click on this pencil and say, you know what, it's not just user data, it is volumes in milliliters, which I'll use since my syringe is demarcated in that. Press OK, and the final thing I want to do is say, you know what, I don't care about time, so I'm going to have pressure versus volume. And it's important to note volume is here in the user entered tab. So I think I'm set up, and it might be natural at this point to say, well, I'm going to start at 60. So let me pull the syringe out, and we still have the start button. So let me hit start, and we have a problem here. Remember, my sample rate dictates how fast data is collected from the sensor, and it's at 20 hertz by default. I can't possibly change the volume in 1/20th of a second between 60 and 55. So I'm going to delete that run by going to our experiment tools, manage runs, delete last run, and show you the final key here is to use a new mode of sampling. By default, new files are in periodic mode, but if I go into our sampling options, I can choose to switch it to manual. And let's see what happens in manual mode. When I hit start, that looks better. I have all the time in the world to collect my first value. So taking my time, I'll put the syringe out to 60 milliliters. Get it on screen for you here. And it's telling me what the current pressure is, but it doesn't record it until I command it. I'm manually sampling. I'm choosing when to do it. I can command it to record the sensor measurement by hitting the screen check mark, or this one down here in the lower left. I'll use the lower left since it doesn't move. And I'll record at 60. The value turns black, indicating it's a recorded sensor measurement. And I'm going to quickly go down the line here because this can be done quickly and we don't have a lot of time. So I'm down to 45. And I'm just making sure I'm going 5 milliliters at a time, lining it up with the current cell of volume. Now, it's inevitable you might make some mistakes, like here's a mistake. Oops, I recorded 35 when it should have been 30. So you can fix it if you go back. I can click on 30 again and say, there's a corrected value. So get down to the last few data points here, 25. It's a little tough after that. You can tell I'm squeezing pretty hard here, 20, and finally 15. All right. All the data points I want now are in black, and there's a ghost value here that's in color. That's the color of the run. That tells me it's not yet recorded, and as soon as I press stop, it goes away, and I have the 10 pairs of data that I wanted here, from 60 milliliters of volume down to 15. So there's probably some relationship here, and we already figured out that we have tools like linear fit, but I alluded to other types of fit. And in this case, I probably want to explore those other fits to see if I can find a relationship between the gas pressure and the volume on the x-axis. So I'm going to open up all the fits here, and I might start exploring inverse square. Looks kind of good. I might look at the mean squared error, 66.8. So let me actually go in here. Can I change it here? Yeah, I can click on this and say, well, it's compared to inverse fit. Look, that mean squared error is much lower, and it looks like it fits a lot better. So quite quickly, I was able to see that maybe I've discovered an inverse relationship here between pressure and volume of a confined gas. Think of how quickly we did that to get some quantitative result here and actually discover this relationship between volume and pressure. So that was a quick investigation using a new technique called manual sampling. We're going to do a couple things with this. One thing I'd like to do is show you yet a third way to get information out of Sparkvue, and that is maybe I'm just interested in this result here and I want to put it in some sort of report. So I'm going to take an operating system screenshot. This varies by operating system. Sparkvue has some tools, but to be honest, it's always quicker to use your operating system. So on Windows, I'm going to press a keyboard shortcut here, Windows Shift S. That's going to allow me to take a screenshot, and I just want to take a screenshot of this graph because that's what I'd like to show in my report. And I happen to have a Word document here. And let me go to the Word document. When I copied it, it is now in my clipboard, and now I can hit Control V to paste it. All right, and it's in my report. Now it's important to note this is just an image. I can't manipulate it further here. It's just a picture of my graph, but this might be what you need if your students are putting it in a Word doc or a Google Sheet or a PowerPoint or putting on a website. I now have an image of that graph. Of course, I might also want to save the file as a Sparklab file if I want to make sure I can always go back to it and do further analysis. So this is gas pressure versus volume data. All right, so quick experiment, but one that allows us to discover some relationships. I'd like to show you a couple more things here, particularly where you can get experiments. In this example, we built the experiment from scratch, and that can be a great way for students and yourself to explore the questions you have with the sensors available to you using Sparkview's displays and tools. But sometimes, in fact, most of the time, you probably don't have the lab time for students to be doing this, especially if they're new to this new technique, for example, manual sampling. So let me show you what we can do. I've already saved this file with data. Wouldn't it be nice if I could save this file and just give it to my students ready for them to collect data? So if you think that's a good idea, I'm going to go ahead and turn off the fit. I'm going to go ahead and delete the data that I collected. Experiment tools, manage runs, delete all runs. And I now have a file that's pretty much ready for them to collect their own data. So I'm going to go to the file menu, the main menu, and choose save as. And I often call these files something like templates or configurations. So if I say that this is gas pressure and volume config, it is a Sparklab that's ready for students to open, connect their sensor, and hit start. And everything about it, from the volumes to the manual sampling to the configured displays, is already set for them. So think about creating your own files if you want to save a little bit of lab time and not have your students do the setup. You can argue there's value in setup, deciding things like sample rates, but sometimes it's not the focus of your class. All right, so final thing we can do is take a screenshot of the display. 3 ways to get information out of Sparkvue. Now, crucially, where can you get labs for Sparkvue? Well, it turns out we have hundreds, many hundreds, maybe 1,000. And here are some of the places you can get them. One is you can build your own, as I just did here with Boyle's Law. Another is built into Sparkvue. I intentionally did Boyle's Law myself here so you can see the build process. But this file I just created, well, it turns out somebody at Pasco already did that. So if I relaunch Sparkvue and I connect my pressure sensor using the path we learned about first today, the sensor data path, as soon as Sparkvue sees that you have a wireless pressure sensor connected, let's take a look at what happens in the lower right of this configuration screen. It says, you have a pressure sensor connected, you might want to use this. And this is a pre-configured file that looks a lot like the one I created with most of the same settings. So that's built into Sparkvue. If I go back to Sparkvue's welcome screen, another thing I can do is look at other labs built into Sparkvue under Open Pasco Experiment. And there are a number of them here across the science, grade levels, and subject areas, and one of which is volume and pressure. If I open this up, it is going to present an entire lab, including instructions to your students. So background information, setup instructions, and most crucially, live data displays. It also has places for students to make responses and enter values in response to questions. So this is what we call Sparklab built into Sparkvue, and that lives inside the Open Pasco Experiment option in Sparkvue. So there are a few labs there, but I want to show you probably the biggest bounty of labs, or by far the biggest bounty, is available in the Pasco Experiment Library on our website. So if you go to pasco.com/free labs, or if you're just on our website, pasco.com, you can get there via resources, experiment library. There are over 1,000 labs in this. And if I go and say, you know what, I'm teaching high school and the concept is Boyle and the product is wireless pressure sensor, it will filter those 104 pages of labs down to the one or few that are relevant to the categories you selected. If I choose Boyle's Law, you'll see that there are a bunch of resources here. We have a set of a document for students to follow. We have an answer sheet for them to write on and hand in. We have sample data for you to look at. If you log into our website with a free account, you will get the teacher files, including background information, sample answers. And for this video, not true of every video, but for a few of them, a few dozen, we have videos that will show you how to collect the data. All right, so hopefully you can see that although you've learned a lot about Sparkvue today, there are resources to help you so that the features you've learned today can just be little enhancements on the resources that are already available for Pasco. So that is the end of our time. Thank you so much for joining us today. If you have any more questions or want some support from our customer service, tech support, or your local Pasco rep, no matter where you are around the world, we encourage you to go to this website, pasco.com/support. Thanks so much for being with us today.